been working with several surveys, but in the past I worked with the theory of dark energy models. And then today I want to tell you about cosmological surveys, and specifically for the photometric case. And I want to show some of the amazing results that people have been obtaining in the last years. But more than this, I want to show to give you a taste of the hard path we have to obtain these results, and how exciting are those times for cosmology, and with these amazing experiments, and what we are planning to the future. So just a small context of the current cosmology status. So our cosmological standard model was settled in the beginning of this century. So it's the lambda CDM, and we have good evidence that we live in a flat universe that is now passing through some accelerated expansion. The gravity is it's described by the general relativity. As far as we could test, general relativity has been able to constrain and to pass through all the different tests. And most of the energy of the universe are made by dark energy in the form of the cosmological constant and the cold dark matter. So these components, the dark energy, are made in more than 70% of the universe. And we have a small quantity of baryonic matter, the matter that makes us and make the stars and everything that we know in Earth. We have a small quantity of radiation and neutrinos that in the past, in the hotter past of the universe, had more influence in the dynamic of the universe. And the bottom line of this model is that it successfully explained a lot of different observations. So that's why this lambda CDM model is also called the cosmological concordance model. This is the cover of the Science in 1998. So this is by the time of the discovery of the accelerating expansion and by observation of supernovae. And although this model can explain a lot of different features, we are having some questions to be answered. So the first one is the detection of the dark matter particle. We have evidence of dark matter since the 1930s, but even though with our best efforts, it's not clear which kind of particle is made in this component of dark matter. So more recently, we have the tensions between the early and late universe. So we have the tensions between the expansions from the local experiments and from the experiments in the early universe. And maybe more important is that 68% of the universe is made by this dark energy. Dark energy, the simplest model is the lambda, the cosmological constant. But if we accept this, we are having a huge mismatch from the theory and the observations. Some authors argue that is the largest mismatch between theory and observation in the history of physics. And this points us that although we have this nice model that has very well understood predictions from our observation, we still need some further investigation and further understanding of the basic and the dominant components of the universe. So we still have a lot of exciting questions to address in cosmology. And one of the experiments, one of the way of tackle these questions are from the cosmological surveys. Today, I want to talk specifically about the photometric surveys. So the idea of this experiment is not observing single objects, but is to observing parts and pieces of the sky and collect as much as data as possible. So in the case of the photometric survey, we want to collect the shape and the position of different galaxies. Also, in comparison to other kind of survey that we have in cosmology, the spectroscopic surveys, we can collect way more information, but on the other hand, our determination of the redshift is worse than spectroscopic, since we are measuring the spectrum of the distance objects using in some different bands. And in order to analyze this large volume of data, but with low redshift resolution, we organize our information in tomographic redshift bins. So we collect the data in the different redshift ranges, and we increase the signal by combining them. So some successful examples of the cosmological photometric surveys are the Hyper Supreme camera of the Subaru experiment, the kilodegree survey, and the dark energy survey. Not surprisingly, I will focus my talk here in the dark energy survey, since I've been working for a few years in this experiment. So here's some properties of the survey. For the dark energy survey, we built the DCAM. The DCAM was the best camera built to the time. It has 570 megapixels. So the survey is a collaboration between several institutions, but led by Fermilab. The DCAM was installed in the Vitor and Blanco telescope in CTIO, Cerro Tololo in Chile. And we had 5 filter bands with a 3 square degrees of field of view. So it means that every time we take a picture with the DCAM, we get information about this field of view. So DES is still analyzing the latest generation of data, but the observation is over. The observation lasted for almost 6 years. We cover 5,000 square degrees. This is more or less 1/8 of the sky. And of course, this is a huge work, and we counted with 400 members. And for the latest generation of the published generation of data, we have more than 30 papers. This number is increasing. So DES made the largest map of the universe to date. This asterisk here is that we now are having the DESI. We are starting with LSST, but for now, we have some very impressive map of the universe. So with this survey, we are targeting 3 big questions. So the main questions are if the late universe and the early universe are explained by the same model. So we are looking for internal constants between different observations of the universe, and we are looking also for tensions between this model, because tensions may point for new physics. So the second question is if the growth of structure and the expansion of the universe agree to each other. So we understand since the supernova that lambda CDM explained very well how the universe is expanding. but we want to understand if the same model that explain the expansion of the universe is enough to explain how the galaxies and the clusters and the other structures in the universe is made. And finally, we want to check if the dark energy density change with the cosmic expansion. So the current model of dark energy, the cosmological constant, is constant. So if we measure some deviation from this equation of state, or if we measure some deviation in the density of the omega lambda or of the lambda, we're gonna maybe looking for a new physics. So in order to achieve this and to answer these questions, we have different kind of probing in the DS. Today, I want to talk more about large-scale structure and the weak gravitational lensing, but I will also mention some efforts in the bioacoustic oscillations in this photometric survey. I know that Jesse gave a nice talk there, so I will focus on some of the results and some of different analyses that she presented. But the basis is basically the same. So the advantage of the weak gravitational lensing is that we can map the dark matter and these fields because the light from this distance source galaxies cross the invisible dark matter field in their way to us. So during this travel, the weak gravitational lens causes a very subtle distortion in the shape of this galaxy that we call the cosmic shear. This is indeed subtle because it's less than 10% of this distortion, the total distortion. So that's why we need to combine images from hundreds of millions of galaxies in order to have a good signal. But the dark matter field is not visible, but we can trace this dark matter through the lens galaxy because we're gonna have some trend of form more galaxies and to have more visible objects around these dark halos. And finally, the combination between the position of the galaxies and the shape of the distant source galaxies is giving us another kind of signal that we call the galaxy-galaxy lensing or galaxy shear. And when the light arrives this very tip of space-time, we can combine this large number of observations in order to have some measurement of the components of the universe. The way that we summarize this information are from two-point correlation. That's the main method of analysis in the DS, but also from the angular power spectrum. So combining the information about two-point correlation, we have combining cosmic shear, combining the information about and the distance about the shapes. The galaxy-galaxy lensing is combining the two-point correlation between the position of a lens galaxy and the source galaxies around it. And finally, we can measure the distance and or in the same fashion way, we can measure the angular power spectrum of the position of galaxies in order to have the galaxy clustering. So this information is way more powerful when we combine everything. This is what we call the 3 times 2-point cosmology or 3 cross 2-point cosmology. Basically, it says that we are combining 3 different 2-point cosmologies in a very careful way in order to have the maximum information given by the survey. So here's this slide. This figure, it was made by Jesse. I always have to show this because this is a brilliant figure, because it's summarizing more or less all the effort of the DES and the other photometric surveys in transform the light from distant objects in cosmological constraints or in our measurements of the universe. So here you can see this figure here. We are collecting information in this patch of the skies, but in this information we can collect different kinds of galaxies, the shape of these galaxies, and we also collect stars. And from the future, we also gonna collect star-linked trails and other spurious objects. So we have some pipelines to get these images and eliminate what's not used for cosmology, for instance, the stars, and keep the galaxies. So with these images of the galaxies, we have this pipelines to measure the shape of the galaxies. In DES, we use the meta-calibration pipeline. That's a way of measuring the ellipticity of these distant galaxies. The other important information that we need is to collect the photometric redshift, so we can know how distant are the galaxies and how to organize them in tomographic redshifts. So we have different pipelines to do this. And we do this by fitting the templates or using some machine learned self-organized map techniques. And finally, this will be the input information for the cosmological analysis. But we need to, before we run our cosmological pipelines, we need to calibrate them quite well. So here in the top, you can see this representation of the simulations. We created a large number of different simulations, between them Buzzer and Flask and Colomox, in order to understand if our pipelines are able to properly analyze this data here. Other important ingredient here is the covariance. The covariance tells us not only how the uncertainty in our measurement, but how we can combine different points of our measurements. Finally, given that, we compare everything with the models, and we finally can get our accurate and measurements of the universe component. I love this figure, but the real life is more complicated, of course. But here is the real pipeline from the DES, and each part of this is a lot of work of different people, and in order to obtain the final results of the cosmological survey. So given the data, we need to produce the catalogs. Given as an example here for the DES Y3 catalogs, this is the latest public version. We have a footprint that's covering a little bit less than 1/8 of the sky. And for the source catalogs, the catalogs of galaxies that we measure the shape, we have 326 million galaxies, and the final cut, using only the galaxies that we trust in the shapes, we reduce this for 100 million galaxy shapes. The density of the galaxy is 5.59 galaxies per arc minute. So each arc minute, we have more than 5 galaxies. And for length catalogs, we have some different catalogs. So for the latest one, the magnitude limited catalog, we kept 10.7 million galaxies, but we also produced another catalog based on the properties of the red galaxies. And we have a special sample from the BAO analysis. So here are our measurements for the configuration space. So in this side here, in the side here, we have the cosmic shear. Here we have the galaxy lengthening. And finally, we have the measurements of the clustering that will be used for the analysis. The gray regions here are the regions of the sample that we are not using for cosmological analysis. This is due because we know that our model are limited and we have some maximum and minimum scales where we can trust in what we are trying to fit. The idea of the DS and of all the cosmological surveys is not only providing very tight constraints on the universe, but more than that is producing reliable and accurate predictions. So that is the trade-off that we have to stress in this kind of work. For the harmonic space, we have these measurements of the cosmic shear and these measurements of the galaxy clustering. We use the similar catalog, but since we have some equivalence between harmonic space and the configuration space, but since we don't have access to all the modes and all the scales, both a kind of analysis has also some subtle difference, and they can isolate different modes in the final analysis. So I will talk very quickly about the BAO detection in the DES. So the BAO sets a standard rule of the universe. And in the DES, in the other photometric survey, we don't have accurate information in the line of sight because we don't have a very accurate information about the redshift. But we have, on the other hand, a large number of different objects, and we can split these objects in these tomographic beams so we can maximize the signal. So here I'm showing the results from our key paper, where we measure the signal of the BAO both in the correlation function and also in the power spectrum. So the detection in harmonic space started in our paper in 2019, where we set this APS for the first version of the APS for using in the DES of the angular power spectrum. And now with this technique and some improvements, we are obtaining a very nice detection of 2.7% in precision by combining the real space, the configuration space information, and the harmonic space information. So here are our results for the DES-Y3.
So what does that mean? Sorry, like so when you say like 4% detection, does that mean like a 25 sigma detection of the BAO? Is that what that means?
Yes, but sorry, I guess I'm missing some information here. This is we have 3 sigma of confidence level detection for the DES. This is the 2.7% is the error bar.
The error bar on what? Sorry, I don't understand.
On this alpha here, this ratio here, we reduce the error bar in our measurement of this distance here. So I'm not joining the details, but we measure the isotropic BAO for the DES. So this is summarizing in a single parameter alpha. That is the ratio between these distances here and the fiducial model. So that's it.
Yeah, and in that plot, it looks like a whatever 20 sigma or something. It's like 0.05 over 1.
It's 4% or 2.7% in that ratio is what you're saying.
Okay, but it comes from like a 3 sigma detection of the DAO feature.
Yeah.
So what that implies is, I mean, it's a very non-Gaussian posterior. Right? So it's only 3 sigma, but it's 4%. So so you cannot really go from signal to noise to a p-value, because at 3 sigma there's nothing basically. Like at 0.5% probability, we have no information whatsoever. But at 68% probability, we have a lot of information. So it's just saying that it's a very non-Gaussian scenario, right?
Yes, indeed. But we cannot, for our data, maybe later I can show you our posterior on alpha. We indeed assume something that's Gaussian close to the peak, and it seems more or less reasonable. Of course, we have some tails, as usually we have in the alpha detection. But I mean, around the peak, I also evaluate the non-Gaussian probability, and it's not quite different. But this is a choice indeed of quote this in terms of this 3 sigma, in terms of the usual Gaussian by the group, I guess, for just for uniformize the information passed. But we have these details in the key paper. Okay. So other important part here is the covariance, and the covariance is crucial to use the data. This is even more crucial when we try to do this multi-probe analysis. So we generate different kinds of covariance, and we check the consistency between them. Here I'm showing the theoretical one that we generated using Cosmology. This code written by Tim Eifler and Elizabeth Krause. And also this is from our Flask simulations. These regions here are just noise, because for this plot here, we didn't use the full set of simulations. But for the DES, we produce like 60 terabytes of simulations in order to make sure that our covariance from the theory was good enough. Also, we performed different tests in the validation. We test if our data was likelihood, the tri-spectrum. We test the effect of having the wrong model in the theoretical covariance, the effects of masking and survey geometry, non-Poissonian shot noise, the beam width, and the galaxy weighting schemes, between others. This is a very extensive paper. And we did a different kind of test by using the linearized likelihood for the goodness of fit. We also did some simple chi-square approach where we get some fiducial data vector, and we compare with the different in the fiducial cosmology. And also we did some parameter estimations and different models of the fiducial cosmology in the covariance. So here we can see that how correlated are the signal. This is even more dramatic here for the shear. So for the harmonic space, the situation is more well contained, since we don't have a lot of leaking between different modes. And for harmonic space, we also test different kinds of covariance. So Cosmology was written to work in the configuration space, so we need to apply and try to other strategies here. So for our fiducial covariance and the shear, we use some method called improved narrow kernel approximation. And for the non-Gaussian part, we use the Cosmology, and we validate everything, use also the Flask simulations. Some similar strategy was done for the BAO, where we have the Cosmology covariance, but we also, I also produce 6,000 simulations for the Flask covariance, and we compare with also the ice column models from the group from Spain. So having all the ingredients, now it's time to go to finally try to measure the components of the universe. So our fiducial and our most central analysis in the DES is the 3x2, as I said before, where we also work with some priors over the nuisance. So a fun story and a hard story is that we only have 7 cosmological parameters for the standard analysis. And we have 23 nuisance parameters that controls the magnification in the case of the shear, controls the bias, controls the error in our photometric redshift, controls how how we stretch the errors, also intrinsic alignment, that's quite important, and the errors in the shear calibration and the source photometric redshift. So I want to show very briefly some results from the DES. First, this is the result from the 3x2. So in gray, we see what this combined analysis is able to perform in measuring the complex of the universe and in measuring the matter density. We quote these two parameters because our survey is more sensitive to this kind of measurement. So in green, we have the measurements from Planck, and since they are not very, we don't have a significant level of tension here, we can combine them and produce this yellowish curve here. Other central result is what we can measure regarding the equation of state of the dark energy. So gray here is again the 3x2. It's not quite stringent, but the combination with Planck and other external experiments shows a better improvement in this constraint of the equation of states. And I will ask your excuse for a second for intermission and tell you about some efforts in the harmonic space. So the harmonic space in the DES is seen as a complementary analysis to the configuration space. We have some advantages in relation to the standard analysis. We have faster measurements. This is dramatically important for new generation of surveys and for using mocks and simulations. Our points are less correlated to each other. If you can imagine, if we have the full sky information, the points would be independent, but since we have some cuts in the area and we have some cuts in some scales, this will induce some mode coupling between different modes. And
Felipe, your audio is fading a little bit, so if you could boost it up a bit more, that would be good.
Okay, can you hear me?
It's faint, but it's very difficult.
Oh, I'm so sorry. I don't know what's happening here.
I think you just have to speak louder.
Yes, I will try to speak louder. Okay, I'm sorry. So on the other hand, although we have this advantage about more well-determined scales, more well-determined correlations, treating this mask of the sky produced by the survey is very challenging because in some case, the mask we have will not work with the current treatment. So we need to do a careful analysis of how the mask is impacting our results in harmonic space. So some of the efforts are summarized here. As I said before, we have the BAO measurement for Y1 and Y3. We have the measurement of the different terms of the angular power spectrum. So the plan is to combine them, and we are already doing part of this. We are now working with the clustering for the Y3 and the shear for the Y3. We have this nice paper written by Cyril discussing the correlation between the configuration space and the harmonic space. And for the future, for the soon future, we want to present our combination of the 3x2 in harmonic space and our comparison to the standard results. So here are some examples on what we have done for the harmonic space. In this paper, we show how we can measure the bias. I guess maybe the most important thing here is that we have a better goodness of fitting to the catalogs than the configuration space did. So we also are having similar results, but they are not equal. And in the red, you can see our results in harmonic space. We can see that we have more cuts here in the low redshift, and it's easier to measure in the higher redshift. In green are the results from the paper by Jack Elvin Poole and the collaborators. The results for the real space, and in blue here are our reanalysis of the same data. So more recently, we produced this paper measuring the shear in harmonic space. We have a good agreement with the configuration space, but our error bars are larger. And now for the next steps, we want to combine the galaxy-galaxy lensing, shear, and the clustering in order to understand how are the results for harmonic space and what difference we're gonna have given our different scales and given our different scale cuts, etc. So returning to the DES-Y3, we have now we are able to discuss the combination with the BAO. So here in gray, I'm showing the standard, in black, it's the standard DS 3x2 plus the supernova data. In blue, in purple are the results combined with the BAO and Planck. And in green dominated here is the Planck results. You can note that BAO and also the BAO from the DS and the DS data itself is not quite sensitive to H0. So the better improvement is always in the clumpness and in the matter density. Finally, since we didn't find a significant tension between external experiment, we could combine the 3x2 in gray, external experiments in orange and purple, and the Planck in green here, and we produce this measurement of the clumpness and of the matter density. And this is the best to the date determination of the clumpness and of the omega matter. So looking to the future, here's this beautiful picture of the LSST. And the LSST will give us a new level of challenge. So LSST is a photometric survey, but the camera is now the best camera built. It has 3.2 gigapixels. It has a 90.64 square degree of field of view and 6 filter bands. And the idea of the LSST is operating for 10 years and observing the absurd number of 20 billion of galaxies. And it will collect 20 terabytes every night and will cover the half of the sky that LSST can measure every 3 days. This is more or less 18,000 square degree in comparison to the DS, for instance, that is between 4 and 5,000 square degrees. So here's the picture of the camera. It's a new picture from this week. We are now doing the commissioning of the instrument. We are now testing how the camera is installed in the instrument. So this base of the telescope weighs 350 tons, and it needs to move really faster, and it needs to point and stop really faster. So before we install this beautiful camera, we've been testing with some mock camera with just heavy weights. So the camera of LSST is really impressive. This is the field of view in terms of the size of the moon. And this is the resolution. If we take a picture of a golf field, you can see the golf ball with this resolution. So the plan of LSST is going to go wider. It's cover a larger footprint. It's go deeper, getting other fainter objects, and finally it's going faster. So it's cover the half of the sky every 3 days in order we can see a lot of transients, a lot of objects in solar system, for instance. So before waiting for the data, we are producing some public pipelines. I'm just saying here, I'm just listing here the ones working for Cosmology that I'm more involved. So we have the core Cosmology library that is providing quick and accurate predictions for the correlations and power spectrum. Firecrown is our likelihood analysis framework. Augur is for the forecast. TXPipe are producing a unified framework for the measurement of ACF and the APS of the angular power spectrum and angular correlation function. And this is also involving the same people that produce a 3-core and a master for the DES and other surveys. And finally, the TJP-COV, this is a provisory name, are producing the theoretical covariance for the 3x2 and also for the combination between 3x2 and the cluster count. This is a group that I've been leading with Carlos Garcia from Oxford, and we are doing nice progress, and we are trying to produce a very user-friendly code, but very accurate with all the domains from the desk. The goal is to having the better measurements of the dark energy equation of states and the better measurements of the growth of the universe. Of course, this is the goal to myself because LSST can produce different nice results in different fields. I'm just focusing here in the cosmology. So some final remarks. I guess my time's over, almost over. So final remarks is that the DS and the other teams have been producing the best cosmological constraints from imaging survey to the date. It's important to stress that these constraints are, we are very conservative in our analysis in order to have the maximum accuracy as possible. The combination of probes are a very rich technique, but it demands a lot of careful work And from the results from the cosmology, lambda CDM model is still alive. We don't have significant evidence of dark energy model, of some exotic dark energy model beyond the cosmological constant. And we don't have significant tension between CMB and large scale structure data in our measurement of the SH parameter. There's a lot of things to say, and this talk is very far to cover everything that's interesting about this kind of experiments. So for the DES, for instance, I've been working with my supervisor, Marcelo Soares Santos, in the GW Cosmology. We have nice works in the extension of dark energy, cluster cosmology, combination with other surveys, and for instance, with other CMB surveys, but also we are working with the combination with the kids. And for the Rubin, a new set of unimaginable problems are coming, but we are happy to be here to try to tackle this, because to scale up very much everything, all the experiments we had up to now. In the first year, we probably will have more data than all the surveys combined in the history. This also means that we have a lot of challenges for data management, for the control of systematics, for better modeling to get other scales. Better modeling also means we're gonna have more parameters to explore in our analysis. It also means more data to analyze and more computational power even to run the theory. But I'm gonna finish with this quote by John Bardeen, that science is a collaborative effort, and the combined results of several people working together is often much more effective than could be that of an individual scientist working alone. This is the truth for our work in surveys, and that this is the truth. This is totally true for the future of the cosmology. So thank you very much for listening to me, and sorry about my sound. Thank you.
Thank you, Felipe. Are there questions? Let me show the full gallery online, so you can see if there's any.
Yeah.
Go ahead.
Thanks for the talk, Felipe. Can you explain again? I didn't entirely understand why were the harmonic space results constraints always weaker than the configuration space constraints?
Yes. Actually, that's not quite true. This was a choice that we did here for the DES for this first round of analysis. And here's the thing. In the paper by Cyril Du in 2020, we tried to estimate the effective number of modes that is entering in the configuration space, and try to translate this for the harmonic space. So given that choice of scale cut, driven by what was chosen for the configuration space, we are having less signal. But for the next round of papers, we are discussing using a different criteria, just comparing the theory prediction and how with a data vector with contamination from baryons and different effects in order to get more scales. So this is a choice for the first set of cosmological analysis, since we are doing some comparative study with the configuration space. This is also not true for the BAO. The BAO, we are having a slightly better constraining for the alpha parameter, but it's really slightly, it's not significantly from the statistical point of view. But that's it. We still have a lot of choices in the how much the signal can enter. Another interesting paper by our colleagues in the LSST is proposing, for instance, a code called Hefty, where they have better constraints using the same data set of the DES, but just going to more larger scales, for smaller scales actually.
Okay, thanks. Other questions? Online too, if you have any, just shout it out.
Well, so I was just curious about, like the slide that you were showing before where you were comparing, like the DES plus Planck to the Planck only, like, with like the purple and yellow contours. I didn't quite, I think the previous one. Yeah, here, sorry. Yeah, so I didn't quite understand. So yellow is Planck only, and purple is Planck combined with DES. Is that right?
Yes. Here's the thing. DES is blurring the 8 knot, but the combination with the Planck is better for the S8. So here, for this axis of the 8 knot, DES cannot tell very much. Our data is not quite sensitive to this parameter. So what we can see some improvement when we look for the S8 in the omega mapper.
Yeah, I guess I'm just trying to understand how the purple contours can be bigger than the yellow contours.
Yes, because basically it's the effect of the black contour here. They are really huge, we are not giving information to Planck. So that's it.
Yeah, that would just make it smaller still. Yeah. If there were two independent, say, Gaussians, you multiply them, still it's going to be smaller than each one of them.
Yes, I see. Yes, I don't know how the correlations are working here.
Too, right?
Mm-hmm. Yes, I'm not quite.
Doesn't have Planck. That is that. Are you sure purple has Planck in it?
Maybe just
yes. Oh, sorry. Yes.
Okay.
I guess maybe this is just the Planck prior, but I need to take a look at this. I don't quite remember how's the covariance here between both probes.
I have a somewhat similar question, which maybe I don't have the numbers completely right, but my recollection is that your value of S8 and its error bars are very similar to what kids find. It's a low 7. Is one of those two numbers from the lensing? If we go back to the lensing, not the BAO, but just the 3x2 point, for example, right? Yeah. So 776. That's similar. I think kids finds 0.76 if I remember. Whereas Planck finds like 0.83 with small error bars. So the kids claims like a 3 to 4 sigma difference, and you say you're consistent. So I've never quite figured out. The numbers seem very similar. I've never quite understood why one group finds consistency and the other doesn't. I wonder whether the Planck error bars are bigger. Maybe you're marginalizing over something else, a more complicated model or something.
Well, so green here, I guess, is Planck, right?
The green is, yes, green is Planck, right?
And gray is DES.
Yes.
Yeah, so they do seem to overlap, right?
They do, but I'm wondering.
Yeah,
I
but,
think
you're totally right. You're totally right. Planck kids has been finding a lower value of S8.
A little bit, but not much, right? It's 7.6 versus 7.7, whereas the Planck number is like 0.83, right?
But the error bar here is 0.17. I know about some recent reanalysis paper that was done. I'm trying to recollect the name now. I can send you later. But yes, Planck has, I guess kids has a slightly smaller error bars. We have been very conservative with the blinding, with the priors, but it's also a smaller number, and these are our results. We test this consistency. This consistency between Planck and DES. You can see by eye, but we also test with different metrics of tensions. So I don't know. I know that kids is doing a different kind of analysis than us. They are using the COSABIS, and they have a different footprint, different redshift selection, different densities. So it's not so easy to compare the work between different surveys.
Other questions? If there aren't, then let's thank Felipe again. Thank you for the talk, Felipe.
Thank you very much.
And too bad you can't be here to share the pizza with us.
Oh.
You'll have to come visit some other time in person.
I'd love to.
All right, thanks again.
Bye.
Bye-bye.